We're going to do one section out of chapter 20, the chapter on electrochemistry. And this is a section on balancing oxidation-reduction reactions. We talked about oxidation states and what redox reactions were in the end of chapter 5. And we're going to learn how to balance those redox reactions. Little bit of review here. We have oil rig. That represents oxidation is loss of electrons. Reduction is gain of electrons. We can also think of it in terms of the oxidation state. Oxidation is an increase in the oxidation state. Reduction is a decrease or a reduction in the oxidation state. In this example, we have calcium reacting with water to form calcium hydroxide and hydrogen gas. The oxygen state of calcium is going from 0 as an element to +2 as the calcium ion here. An increase in oxidation state, so calcium is being oxidized. The hydrogen is going from a +1 in water to 0 as an element. Oxidation state's going down. That's the reduction. So in redox reactions, the mass has to balance, and that's what we've been doing previously in balancing by inspection. But the charge also must balance. And for some of these reactions, if you try to balance them by inspection, you're going to pull your hair out because it's just almost impossible. Some of them you can do it that way, but I'm going to show you a method called the half reaction method of balancing redox reactions. So what we do here is we take the equation we're given and we break it into two half reactions. One for the oxidation, one for the reduction. We balance those individually, and then we add them back together. Because we have to make sure that the electrons lost in the oxidation are the same number as the electrons gained in the reduction. Because the electrons are being transferred from one thing to another, we can't be gaining or losing electrons. I guess you could call that conservation of electrons. So this procedure has several steps. There goes the train. I'm leaving the door open because it's actually warmer out there and it's really cold in here. The first step of assigning oxidation states and identifying the things that are being oxidized and reduced, that's a good idea, but it's not absolutely necessary. So we can start at step 2, separate the overall reaction into two half reactions, balance each half reaction with respect to mass. And we're going to balance everything besides hydrogen and oxygen first. Then we balance oxygen by adding water, and we'll balance the hydrogen by adding H+. It seems like we're just throwing new things into our equation, but we're not, because this is an aqueous reaction. That means it's swimming in lots and lots of water. So can water participate? Sure. And it's an acidic solution. When acids dissolve, they form hydrogen ions. So there's also hydrogen ions around, so we can bring those into the equations as needed. After we finish that, we balance with respect to charge, and we do this by adding electrons. We want to make sure the sum of the charges on each side of the arrow for each half reaction is the same. It might be 0 on both sides, it might be +2 on both sides, it just needs to be equal. After we do that, we need to make sure that we have the same, the same number of electrons in each of the half reactions. Sometimes it just comes out that way, hooray. Other times it doesn't. And so then we're going to multiply the coefficients by a small whole number in order to get the same number of electrons. Hopefully that will make more sense when we do it. Then we add the two half reactions together. The electrons will cancel out because that's what we're setting it up to do. And sometimes you can cancel out other things like water or something. And then you should always verify at the end that your reaction is balanced. Go through and look for the number of atoms of each element, and then also make sure that the charges are the same on both sides. So let's do an example. We'll start with some simpler ones and go to a little more complicated. So what I've done here for this first one is I've made a very brief list of the steps that we're doing over here, so we can kind of refer to them. So this says balance the redox reaction in acidic solution. So we could assign it oxidation states. Let's just do that for fun. What's the oxidation state of the hydrogen ion? +1. If it's a single ion, a single atom ion, a monatomic ion, the charge is the oxidation state. What about the chromium here? 0. It has no charge. That is, the element is 0. Over here, H2. 0. Because if we look at this H2, all of the oxidation states in there have to add up to the charge on the molecule, which is 0. So each of them has to be 0 because you're not going to get one to be +1 and one to be -1. They're going to be the same. Or you can remember this is an element. Elements always have oxidation states of 0. And how about here, this chromium 2? This is +2. So here we're going from +1 to 0. Is that oxidation or reduction? That's reduction, because the oxidation state is being reduced. And this is going from 0 to +2. That's our oxidation. So that was just, kind of good review. So separate into two half reactions. If we look at our reactants and products, we'll see that there's fairly obviously two pairs. This hydrogen ion and the H2 gas are pretty similar to each other, right? They've got the same elements. And then I've got this chromium as an atom and chromium as an ion. So, we're not going to be able to turn H plus into Cr2 plus, right? So we just split them up so that the like things are together. Doesn't matter which one you do first. I usually start with the first thing. We want to write these out so that the arrows are lined up. So I'm going to have H plus aqueous going to H2 gas. And I like to leave a little space because sometimes you need to put coefficients in there. So that's the green ones. And then the other part of it would be this chromium solid to chromium 2 plus. So we have one half reaction for the reduction and one for the oxidation. So that's step number 2. We did number 1, we did number 2. Balance the half reactions with respect to mass. Other elements first, then oxygen, then hydrogen. Well, here, there aren't any other elements. There's no oxygen, there's just hydrogen. So how can we balance this? We need a 2 in front of H plus. So we have 2 hydrogens and 2 hydrogens. We worry about the charge in the next step. How about this one? That one's already balanced, right? Sometimes that happens. Okay, so that was step 3. Now we will balance with respect to charge. We do this by adding electrons. So if I look on the left side of the arrow, this equation has +2 on the left side and 0 on the right. I need them to be the same, and the only way I can change anything is by adding negative charges. So if I add 2 electrons to this side, 2 negative charges and 2 positive charges add up to 0, which is equal to the charge on the other side. We also see that reduction is what's happening here. Reduction is gain of electrons. The hydrogen ion is gaining electrons. It's being reduced. What will happen in these 2 half reactions, whether you identify this stuff or not, one will have electrons as a reactant, one will have them as a product. Down here we've got chromium with a 0 charge and chromium with a positive 2 charge. They just need to be the same on both sides. So I'm going to add electrons over here because, again, the two negatives and the two positives will add up to 0, which is equal to the overall charge over there. Balancing with respect to charge. Any questions yet? Make the number of electrons equal. Well, this one has 2 electrons, and that one has 2 electrons. They're already equal, so we don't have to do anything. Add the half reactions together. So let's add these together. Just adding those. And here we have 2 electrons on one side and 2 electrons on the other side. When we add that, those will cancel out. Yes?
If the number of electrons weren't equal, how would you?
We would have to multiply all the coefficients, and we'll do an example of that. So here, this is gaining 2 electrons, that's losing 2 electrons. The electrons are not going to show up in the balanced chemical equation. They're always going to cancel out because that's how we're setting it up. So we cross out the electrons, we write down what's left. So I have 2 hydrogen ions plus chromium metal is going to make hydrogen gas plus chromium 2 ion. Add them together and then verify. 2 hydrogens, 1 chromium, 1 chromium. On the reactant side, a total of positive 2 charge. On the product side, total of positive 2 charge. Any questions? That was a very simple example. We didn't have to do some of the steps. We'll do several examples and we'll add those in. So here's another one. Here we have iron 2 reacting with permanganate ion to form iron 3 and manganese 2 ion. So what's the first thing we have to do? That's the first thing we can do. Maybe we should do it, but we don't actually have to do it. Separate into half reactions. So here's iron. What's the thing on the product side that's going to go with that? The iron 3, right? And then the MnO4 minus and the Mn must go together. So we'll write our 2 half reactions. Again, we're going to be lining up the arrows. So Fe2 plus is going to turn into Fe3 plus, and MnO4 minus is going to turn into Mn2 plus. Well, that's a good question. Where do those 4 oxygens go? That's why when we balance these for mass, we end up using water and hydrogen ions. Because you can't balance this one by inspection, can you? Because they're like, well, the irons and the manganese are fine, but this side has 4 oxygens, that side has no oxygens. There's no coefficients that you can throw in there that are going to fix that. Because in a lot of redox reactions, water participates, but you don't see it from that. Yes? Oh, no, you're just waving your pencil at me.
I am.
Mm-hmm. Okay, so what do we do next? We're going to balance for mass. 1 iron and 1 iron, already good. Here, I want to do the manganese first and save oxygen for later. So 1 manganese, that's good. But here's our problematic 4 oxygens. We have to add something in on the other side that has oxygen in it. We're going to use water because this is an aqueous solution. There is water in the solution. So I'm going to add water over here. Water's a liquid at room temperature. And in order to get 4 oxygens, I'm going to need 4 water molecules. okay? Then we balance hydrogen, because by doing this, we fixed our oxygen problem, we introduced a hydrogen problem, right? So I've got 2 times 4, I've got 8 hydrogens in here, and we're going to balance the hydrogens by adding hydrogen ions. This is an acidic solution. There are hydrogen ions in there. So I need 8 hydrogen ions to give me my 8 hydrogens. Any questions? You know, this is a step you just have to remember. I'm going to balance oxygen with water. I'm going to balance hydrogen with hydrogen ion. What's the next step? Balance the electrons, balance the charge. So here I've got a positive 2 charge and a positive 3 charge. Where should I put the electrons? On the product side, right? And I just need 1, because this -1 and the 3 together is positive 2, which equals positive 2. And it's actually a good idea to do that on your calculator, because sometimes our brains do funny things with these simple positive and negative numbers, right? So it's entirely fine to use your calculator for that. And then down here it's a little more complicated. Here we have 8 positive charges and 1 negative charge. So what's that overall charge? +7. And over here, I've got a total of +2. So the difference between these is 5, right? So if I put 5 electrons on this side, I can bring the overall charge. So I've got -5 and +7, and now I've got +2. Okay? What's the next step? We need to get the same number of electrons. So this is my oxidation. Electrons are being lost. This is my reduction. Electrons are being gained. But I can't lose 1 electron up here and gain 5 down there. So I need to find the lowest common multiple between 1 and 5, which happens to be 5. So if I multiply these coefficients by 5, then I'll have 5 electrons, and it will still be balanced, because I'm just making more of everything. So I have to have 5 of these things happening to give me the 5 electrons so that this reaction can go. Then we're going to add them together. Well, what's going to cancel out? The electrons, right? We'll cross those off. We're not going to write those down. And then let's write the other things down. So I've got 5 iron 2 ions. And I've got 8 hydrogen ions. And I've got permanganate ion. And that's going to give me 5 Fe3 plus Mn2 plus 4 H2O. I know. Oh, just wait till you see one of the other ones. I'm building you up. I don't want to scare you. So we can check this, right? 5 Fe, 5 Fe. 8 H's, 2 times 4, 8 H's. 1 Mn, 1 Mn, 4 oxygens, 4 oxygens. And we can look at the charges. So this is 5 times 2 is positive 10 and positive 8, right? So we've got 10 plus 8 and then minus 1. So that's what, plus 17? Over here, I have 5 times 3, which is 15, and a positive 2, and nothing on the water, and so that's also plus 17. Any questions? Let's do another one. Copper and nitrate. This is the redox reaction that occurred when we dissolved that copper wire in nitric acid. The NO2 gas here, that's that brown smoke that we saw coming off. So let's break this into half reactions. I'm just going to start with the first thing, which is copper. And which of the products belongs on the other side of this arrow? The Cu2+, right? It's the one that's most similar. And so my other reaction will be NO3 minus, and that must turn into NO2 gas. Next, we balance for mass. 1 copper, already balanced. Here, we're going to balance everything but oxygen and hydrogen first. So here we have 1 nitrogen and 1 nitrogen. Then we balance oxygens. There's 3 oxygens here and only 2 over there, and without throwing water in here, there's no way you can balance this. So if I add H2O over here, now I can have my 3 oxygens, and there's 3 oxygens. And we're not making stuff up here because it's an aqueous solution. There's like so much water compared to how much nitrate there is. That's our mass balance. Then we do our charge balance. So here we've got 0 on this side and plus 2 on that side. Where do I put the electrons and how many do I need? I'm going to need 2, and I need to put them over here, yeah? 2 negatives, 2 positives, overall 0. Down here, oh man, I did this yesterday too. What did I forget? I forgot to balance the hydrogens. And what alerted me to this is I'm looking at the charges and thinking, that's telling me to add an electron over there. That's wrong. Because you have to have electrons on the product side for one and on the reactant side for the other. Forgot the hydrogens. 2 hydrogens down here. So we're going to balance that with 2 hydrogen ions over here. Now I have 0 charge on the right, and I have plus 2 and minus 1. I have a total of plus 1 on the left. So here I'm going to need just 1 electron to balance the charge. My number of electrons is not equal. Here I've got 2 electrons, and down here I only have 1. So I'm going to multiply the equation that doesn't have enough electrons by a factor to make them equal. So here I have 1. If I multiply everything by 2, then I have 2 electrons. I also have 4 hydrogens, 2 nitrates, 2 NO2, and 2 H2O. It's still balanced because I did the same thing to everybody. Now we can add this together. And I've got 2 electrons on the product side and 2 electrons on the reactant side, so those cancel out. So Cu solid plus 4, H plus aqueous plus 2, NO3 minus aqueous. It's going to make Cu2+. 2 plus aqueous plus 2 NO2 gas plus 2 H2O liquid. Any questions? What if the solution's basic and not acidic? We have to add one thing. So we're going to neutralize hydrogen by adding enough hydroxide to neutralize the hydrogen ions, and then we'll add the same number of hydroxide ions to each side of the equation to do that. So we'll go through the whole balancing thing. We'll get a balanced in acidic solution equation, and then we'll get rid of the hydrogen ions by neutralizing them. Because if I have, say, 2 hydrogen ions and I add 2 hydroxide ions, what do I get? Water. I get water. I get 2 water molecules. And so the acid part is gone. So that's what we're going to do. Balance the redox reaction in basic solution. Same steps. Make half reactions. I minus to I2. Because these are the most alike. And then we've got permanganate again. This time it's going to MnO2. So MnO4 minus going to MnO2. Balance the mass. Here I have 1 iodine, and there I've got 2, so I need a coefficient of 2 in front of the iodide. Down here I have 1 manganese and 1 manganese, but one side has 4 oxygens and one has 2. So I balance the oxygens by adding water. I need 2 water molecules to give me 2 oxygen atoms. And then, not forgetting, like I did on the last example, we have to take care of the hydrogens that we just threw in here. 2 times 2, 4 hydrogens. So there's going to be 4 hydrogen ions on the other side. We balanced for mass, now we balance for charge. This side has 2 negative charges, the other side is 0. So I need 2 electrons over here. If you do that optional first step, you look at, okay, well this is -1 and that's going to 0. This is the oxidation, so I'm losing electrons. That tells you they're going to go over here. But just looking at the charges, you'll also come up with the correct place and number of electrons. Second reaction, this side is all 0, and this side we have +4 and -1. That gives me +3. So to make it be equal to this side, I need 3 electrons. The next step is get the number of electrons in each half reaction to be the same. What's the least common multiple of 2 and 3? 6. 6 is the smallest number that both 2 and 3 are factors of. We could do higher, but then we'd end up having to simplify at the end. So we're always looking for the smallest one. So I'm going to multiply the top equation, all the coefficients, by 3, and I'm going to multiply the bottom ones by 2. And I write these over here because as you're going across, it's so easy to forget what you're doing. So 3 times 2 gives me 6 of those. Here I'm multiplying by 3, so that's just 3, and this one is going to be 6. Down here I'm multiplying by 2, so 2 times 3 is 6. And multiplying this by 2, I get 8. And 2, and 2, and 4. They should still be balanced for mass and charge. Now we're going to add them together. Six electrons and 6 electrons go away. So I'm going to write down what I've got left. Got 6 I minus plus 8 hydrogen ions plus 2 permanganate ions. And that's going to make 3 iodine molecules and 2 MnO2 and 4 H2O. If the question was balanced in acidic solution, this would be the answer. But they want basic solution. In a basic solution, you don't have hydrogen ions floating around, you have hydroxide ions floating around. So the way we fix this is I check out the hydrogen ions. I've got 8 hydrogen ions. I need to neutralize those. So I'm going to add the same number of hydroxide ions. Because 8 hydrogen ions plus 8 hydroxide ions is going to give me 8 water molecules. But I spent some time balancing this. I don't want to screw it up. If I add 8 hydroxides to that side, I need to add 8 hydroxides to the other side also. Plus 8 OH minus. So these guys together become 8 water molecules. Now this is a point where there's probably going to be water on both sides. I've got 4 water molecules over here. I've got 8 over there. We don't usually have exactly the same thing showing up on both sides of our balanced chemical equation. So what I'm going to do is I'm going to subtract 4 water molecules from both sides. So I'm left with 4 H2O. And over here, 4 H2O minus 4 H2O is 0 H2Os. Now I have no room to write my answer. That's now 4 H2Os. So 6 I minus plus 4 H2O liquid plus a train whistle plus 2 permanganate ions plus another train whistle. You have to have one on both sides of the arrow. That's just way too many. Apparently I offended him. Good grief. Six I's, 2 times 3, 6 I's. 2 times 4, 8 H's, 8 H's. Here's 4 oxygens and 8 oxygens, that's 12. And over here I have 4 plus 8 is 12. 1 manganese, 1 manganese. Total charge, got -6 and -2, so -8, and -8 over here.
I got lost around what we did to the
What, up here?
What we did to the 8 hydrogens
To get the 4
4
H2Os?
waters.
Okay, so I added the 8 hydroxides,
Okay.
and the 8 hydroxides and the 8 hydrogen ions became 8 water molecules.
Okay.
Then I subtracted 4 water molecules from each side. So subtracted all of these, and that brought this down to 4 from 8. Yeah, that's a good question.
Why do we subtract the 4?
Well, because in our balanced chemical equation, we don't have stuff that's the same on both sides. You could think of those as spectators, I suppose. But I could throw 3 molecules of opium in here and 3 molecules of opium over there. Would it be balanced? Yes.
So they're just not needed
They're not needed.
for the reaction. Okay.
So there should be one correct balanced chemical equation. Lowest coefficients, no extra stuff. Because if you're going to put extra stuff, you can do anything. You can put train whistles in there. You have a question?
You just subtract the excess H2O on the right side.
Yeah, so I had 4 H2Os here, and I had 8 over here originally. I should have planned ahead a little better. So over here I had 8 waters. On the other side I had 4. And so if I subtract 4 from both sides, I end up with 4 over here and 0 over there.
Are you always going to have more H2O on the side?
Not necessarily, no.
So you just subtract by the least.
Yeah. Whichever one has the fewest, just subtract all of those. Some people will do, will take care of their hydrogen ions up here, and then they'll cross out waters before they add them together. But I think it's best to just do the whole, pretend it's an acidic solution, and then fix it to be basic.
I don't know why it's not clear with me. When you add the 4 water sorry,
Mhm.
4 water molecules and you add the 8 hydrogen molecules, what do you get when you add those together?
Okay.
I don't know why I can't.
No,
comment
no.
on that.
So, if I should have started up higher, I ended up writing this out a little differently than I did. Just bear with me. It was here. There. That's what we were doing. So 8 hydrogen ions, we added 8 hydroxide ions. And we added 8 hydroxide ions over here. So those gave me 8 water molecules. Then I'm subtracting 4 water molecules from this side and 4 water molecules from that side. So this is like if you had an equation that was 2x equals 5x. Well, you can subtract 2x from both sides, right? Well, let's pretend there's an a plus over here. A plus 2x. So that ends up being 0. So I've just got a is equal to 3x. So chemical equations behave much like math equations, where you can add the 2 equations together, you can remove stuff from both sides, you can multiply or divide. Any other questions? There's another one. So here we've got chlorate, hypochlorite ion, and CrOH4 negative, which is not something we learned how to name. ClO minus. And that's going to turn into the chloride. And then CrOH4 minus is going to become CrO4 2 minus, a chromate ion. Half reactions. Balance for charge. balance for mass. So up here, 1 chlorine and 1 chlorine. That's good. Reactant side has an oxygen, and so to balance oxygens, I'm going to add water wherever I need it to balance that. So by adding a water molecule over here, now I have 1 oxygen on each side. But now I introduced hydrogen, so now I have to balance that. So 2 hydrogens over here means I'm going to need 2 hydrogen ions over there. Everybody okay with that? Down here, for mass, 1 chromium, 1 chromium, 4 oxygens, 4 oxygens. Oh, that was convenient. The hydrogen's the only one that's not balanced. So there are 4 hydrogens on the left side. So I need to add 4 hydrogen ions on the right side. So all my letters are balanced. Now I balance charges. So up here I have +2 and -1. +2 minus 1, so that equals +1. And on this side, I have -1. How many electrons do I need to get +1 to -1? I need 2. So I add 2 electrons here. I've got -2 + 2 minus 1, and now that equals -1, which is the same as I have over there. That makes things hard to look at later. Down here, 1 negative charge on the left side, and I've got stuff all over the place over here. I have -2 + 4. All right, so that's +2. -2 and 4 positive charges. Here I have +2, here I have -1. How many electrons do I need?
3.
I need 3. I need -3 here, and that'll give me -1. I highly encourage you to make some little notes like this somewhere, because, if I had money riding on this, I would do that. I wouldn't trust it in my head. It's easy to mess up. Okay, we balanced for mass, we balanced for charge, we need to get the equal electrons. Oh, we got the 2 and 3 thing again. So we multiply the top by 3, we multiply the bottom by 2. We're going to get 6 electrons on each side. So this gives me 6, and 2 times 3 is 6, and it's 3 and 3 and 3. The bottom goes by 2, so 2 of those and 2 of those. 2 times 8, 2 times 4 is 8, and this is 6. Add them together. We've set it up so that we have 6 electrons on one side, 6 electrons on the other side. You cross those out. We've got 6 hydrogen ions here and 8 hydrogen ions there. We could fix it now, or we can fix it later. Let's fix it later. Not super later, but a little bit later. So 6 hydrogen ions plus 3 hypochlorite ions plus 2 CrOH4 minus ions going to make 3 chloride ions plus 3 water molecules. Yeah, plus 2 chromate ions plus 8 hydrogen ions. It still didn't fit. It was closer. I could make it, but it would take too long. It's not worth it. This is a little easier to look at than all of that. We had crossed coefficients out and everything. So here we have 6 hydrogen ions on that side and 8 hydrogen ions on that side. So we want to reduce that number. So whichever side has the smaller, we're just going to subtract those. So I'm going to subtract 6 hydrogen ions on this side so that I get 0. And I'm going to subtract 6 hydrogen ions on this side, and I'll be left with 2 hydrogen ions. So the highlighted stuff is what I still have. I don't know if that's helpful or not. Dang it. Look at that. Sorry, I'm having fun. Yay! So all I did there is I copied the highlighted parts and put them all together. That might not have been faster than just writing them over again, but it was fun. I learned a new thing. That is the correct balance equation for an acidic solution. How do we do it for a basic solution? Yeah, we have to get rid of the hydrogen ions by adding hydroxide ions. So I have 2 hydrogen ions over here. Let's see, what color haven't I used? Orange. So I'm going to add 2 hydroxide ions. That will give me 2 water molecules. And I'm also adding 2 hydroxide ions over there. So I've got these guys and the hydroxide, and then over here I have the chloride, the chromate, and I have water here and I have water there. So I want to put those together. 3 3 waters plus 2 waters is 5. I have just enough room down here to write the answer. If you're a person who writes big, you might want to turn your paper sideways when you do these, so you get a longer piece of paper. Wasn't that fun? No, it probably felt like I was just sticking needles in your eyeballs or something. Yes?
Does it matter where the OH is situated?
No, it doesn't. So I put it last here. You could put it first because 3 plus 2 is 5 and 2 plus 3 is also 5, right? And so the order that these come in doesn't matter. And even Mastering Chemistry understands that. It's really picky about some things, but it gets that. Any other questions? So the good news is this is not a big deal, okay? This is not a big deal in Chem 1A. So balancing chemical equations, not like this, just by inspection, that's kind of a big deal. Stoichiometry, very big deal. Molar mass, big deal. So if you're struggling with some of those things, focus your efforts, your energy on the things that are big deals, okay?